Hello, Nick Leifker here, and welcome again to Management 409, Operations Management. We started by talking about projects and what projects are basically and what they're all about. So here's the question. How do we manage a project? How do we see what steps in a project need to occur at what times? Well, also, how do we know how long it takes to complete the project? Well, all of these things can be answered. So we have information to gather, a list of tasks that need to be performed, as well as an estimate of how long each task will take. Well, what we can do with this, we have a nice little tool that lets us get from where we are to where we want to be. Nice little tool called PERT CPM, and it's this that will give us the information we need to manage our project, to complete our project on time. And so that is the subject of this lecture today. How do we use PERT CPM? What are the tools by which we figure out what tasks need to occur at what time? What is largely going to determine what tasks need to occur when is a nice little tool called PERT CPM, and more specifically, the fact that each task, well, needs to be done in somewhat of an order. In other words, before you can build the roof of the house, you have to build the frame of the house. Before you build the frame of the house, you have to build the foundation. So things need to happen at a certain order. So because you have these preceding tasks that need to be completed before other tasks can start, this means that when a project is completed, that it is done in a certain sequence. A good example, this class. To complete this class, or more to the point, to take this class, you need to have taken Econ 106C, economics. You need to have taken Econ 221, which is statistics. And you need to have taken some sort of math course, either MSTI 130, ideally MSTI 130, or Math 112 or 120. So before this task could be completed, there were several preceding tasks that needed to occur. So when it comes to managing a project, you need to look at the list of tasks and see which tasks need to occur before other tasks can start. Now, why do we call it PERT CPM? Well, the reason why is because two groups developed almost identical techniques separately, and each called it something different. PERT, Program Evaluation and Review Technique, CPM, Critical Path Method. That said, you will probably find in the book two different techniques used with PERT CPM. One known as activity on node, the other known as activity on arrow. And you'll see these every so often. That said, what we are going to learn in this class is activity on node. And there is a very good reason why. Activity on arrow is a kludge. Activity on arrow, in order for it to work, some things are added to the technique that frankly are superfluous. As a result, well, basically what is added is, if you will, phantom arrows. And I really don't like that particular technique. In other words, to make it work, some things are added to activity on arrow that I don't think are really conductive to what we need to do. So, in this course, we are going to use and we are going to learn activity on node. So, that said, with PERT CPM, we have the tasks, we have the amount of time that each task takes, we have a list of prerequisites for each task. So now what? Well, the first thing that we would do after that, once we have that information, is we would develop a project flow map. And project flow map is just a visual representation of the project and its tasks, with arrows representing the relationship between each task and its prerequisites. Basically, we represent each task as a node and the relationship between those tasks as arrows. So, what is answered by PERT CPM? What questions are answered by PERT CPM? Well, we get the completion date, how long does it take for this project to get done? We are able to see if it's on schedule and within budget while the project is going on. We get to see what activities are critical. In other words, which activities are going to really determine how long this project takes. We also get to see if there's enough resources available. We see how to finish the project early at the least possible cost if those tasks can be hurried, and we'll talk about crashing toward the end of the chapter. And we also can get the probability of completing the project by a given date if there's uncertainty in the task completion times, and there's almost always uncertainty in the task completion times. So this is the information that PERT CPM gives us. Now, how we represent a task within PERT CPM is with a node, and a node looks a lot like this. Now, you'll note that we basically have an oval. If you want to use a rectangle, you can, but you basically have those 6 compartments. And what those 6 compartments represent is, well, they represent different aspects of that task. We generally use letters to indicate which task. Reason why is because, frankly, there are more than enough numbers floating around. It's a good idea to use letters to represent each task as such. We also have the task length, how long this particular task takes. If we are using PERT CPM with uncertainty, this would be the mean task length. So this is how long that particular task takes. And then in those corners, we have the earliest start time and earliest finish time, which is the earliest that task can start and finish. And we also have the latest start and latest finish time. Now, what the latest start and latest finish time are, these are the latest that these tasks can start and finish without delaying the project. It is possible for the task to start and finish later than that. However, it just means that the project is going to be delayed. Now, you'll note something here. Just looking at the numbers here, what is 7 plus 5? That's 12. That's how we calculate the earliest finish time. The earliest finish time is just earliest start time plus the task length. In the same way, that latest start time, in order to calculate that, that's just going to be the latest finish time, that's 16, minus the task length. Because when we calculate latest start and latest finish, we go backwards through the project. So this is a node. This is something to be done. This is a task. This is what we use to represent tasks in PERT CPM. Now, for base PERT CPM, there's 3 steps. And when we get to PERT CPM with uncertainty, there's going to be a lot more. We basically add on to these steps. But for basic vanilla PERT CPM, there's 3 steps. Step 1. Well, step 1, you draw the project flow map. So you place each step in the project flow map from beginning to end with arrows pointing from predecessor to successor so that you represent each task as a node and you have the arrows representing the relationship between those tasks. So, step 2. In this case, we go forward through the project and determine earliest start and earliest finish time for each step in the project. And then for step 3, in this case, we calculate the latest finish and latest start of each task by going backwards through the project. Now, it's important to note that once you have the earliest start and earliest finish time for each step in the project, you know how long the project is going to take. That determines the expected completion time for the project. However, there's more to managing a project than just knowing how long it's expected to take. So, step 1, go forward through the project to draw the project flow map. Step 2, go forward and determine the earliest start and earliest finish time for each step. And step 3, go backward through the project to calculate latest finish and latest start. So, let's work through an example here. We have 6 tasks, lettered A through F. Each task has a length of time. Task A takes 4 weeks, for instance. Task B takes 5 weeks. And each task has a set of predecessors. Task A and B can start right away. Task C has A for predecessor, so before C can start, A has to finish. Task D has both B and C for a predecessor, so before D can start, both B and C have to have completed. So we have our tasks, we have our length of time, we have our predecessors. So the first thing we need to do is we need to draw out the project flow map. Now, nothing is waiting on A or B. Those tasks can start immediately, can start right away. So we draw our node for A, our node for B, and we draw an arrow from start to A and from start to B. I find it generally good practice to put that start there, and as you'll see later, to put that finish there, because, well, it's a good idea to know where you start and where you end. So we start drawing our project flow map. We start by drawing those beginning tasks, the ones that nothing is waiting on. Well, we continue down the list. So task C, well, it has A for a predecessor. So we draw C on our project flow map, and we go from A to C. Keep in mind, when we do this on paper, well, first of all, it's a good idea to draw it using landscape format rather than portrait, because this is a case where you can run out of real estate really fast. So you draw next task C, and then because C has A for a predecessor, you draw an arrow from A to C. So we continue. We draw D on our project flow map. Now keep in mind, D has two predecessors, both B and C. So we draw D on our map, and then we draw an arrow from B to D and from C to D. We continue drawing the project flow map, so we put E on our project flow map. E has C for a predecessor, so we draw the bubble for E, and then draw an arrow from C to E. And then, finally, we draw F on a project flow map and draw an arrow from D to F, because F has D for a predecessor. Now, it's important to note that E and F, these are the final tasks. Nothing is waiting on E and F. Nothing has E or F for a predecessor. So, a good way to finish things off is to draw a nice little bubble marked finish. And because nothing is waiting on E or F, we draw an arrow from E to finish and an arrow from F to finish. This is, again, generally good practice when it comes to drawing a project flow map. So, that's step one. We've drawn the project flow map. So once we have that, it's time to use it. It's time to go through that project flow map and determine the earliest start and earliest finish time for each task. This is, as you'd expect, the earliest that step in the project can start, and the earliest that step in the project can be completed. Now, because the beginning tasks, the ones at the very beginning, there's nothing that they're waiting on. So they can start right away. They have an early start time of 0, and that is where you start determining your earliest start and earliest finish. So with those beginning tasks, it has an early start time of 0, and from there you go through the project and calculate earliest start and earliest finish. The earliest finish is just the earliest start plus the task length, and the earliest start is the largest of the earliest finish times of all predecessors. So you look at the predecessors for that task, you see their earliest start times, or earliest finish times, and the largest of those becomes the earliest start time for that task. So, as mentioned, we start at the beginning. Since A and B are at the very beginning and they are waiting on nothing and can start right away, they have an early start time of 0. So, that becomes the earliest start time for A, that becomes the earliest start time for B. Now remember how we calculate earliest finish. Earliest finish is early start plus the task length. So for A, 0 plus 4 is 4. For B, 0 plus 5 is 5. And these become the earliest finish times for A and B, respectively. So, A has an earliest finish time of 4, B has an earliest finish time of 5. Let's go on. Now for task C, well, task C has A for a predecessor. So since A has an earliest finish time of 4, that becomes C's earliest start time. So C has an earliest start time of 4. We can now calculate its earliest finish time. For C's earliest finish time, again, that's earliest start time plus task length. So 4 plus 3. 4 plus 3 is equal to 7, of course, and this becomes C's earliest finish time. Now for D, it becomes kind of interesting because D has both B and C for a predecessor. So what is D's earliest start time? Well, you recall that the earliest start time for a task is the largest earliest finish time of all of its predecessors. So let's see. B has an earliest finish time of 5. C has an earliest finish time of 7. What's the larger of these two? Well, the larger of these two is 7. So that becomes D's earliest start time. Again, we look at the largest earliest finish time of all of the predecessors to see the earliest start time for that task. So D's earliest start time is 7, the larger of 5 and 7. So we go on. So D's earliest start time is 7. 7 plus 3. This becomes D's earliest finish time. So D's earliest finish time is 10. So we go on. So E has C for a predecessor. So C's earliest finish time of 7 becomes E's earliest start time of 7. And D has F for a predecessor, so D's earliest finish time of 10 becomes F's earliest start time of 10. Well, once we have this, it sort of becomes straightforward. E's earliest finish time, 7 plus 5, this is equal to 12. F's earliest finish time, 10 plus 3, this is equal to 13. And so we now have the earliest finish times for both E and F. Well, we now have the earliest start and earliest finish times for all of these tasks. So what's the completion time? What's the finish time? Well, if the earliest that E can finish is 12 and the earliest that F can finish is 13, well, we're not going to be able to finish before all of it's done. So that largest finish time of 13 weeks, that becomes the finish time for the project completion time of 13 weeks. So we now know how long it's going to take to complete this project. And we've figured out the earliest start and earliest finish time for each of these tasks. This does not mean, however, that we're done. We still need to figure out the latest start and latest finish times for each task for reasons that will become apparent. You see, the earliest start and earliest finish times, this is the earliest time possible to start and finish each task, and that's nice and beautiful and all, but sometimes tasks get delayed. So what we also need to figure out is the latest start and finish times. Specifically, the latest times possible to start and finish a task if the project is to be completed by the expected time. In other words, if we're going to meet that completion time that we saw earlier. Now, it is possible for us to start and finish a task later than that. However, it just means that the project is going to be delayed. So, to calculate the latest start and latest finish for each task, well, we start at the end, where we have the project completion time that we just found, that 13 weeks. This becomes the latest finish for all of the end tasks because, well, nothing's waiting on them. Once they're done, once all of those are done, the project's done. So this becomes the latest finish, that 13 weeks becomes the latest finish time for all of those end tasks. The project completion time becomes the latest finish time for all of those end tasks. And from there, we calculate the latest finish and latest start as follows. The latest start for each task is just the latest finish minus the task length. And the latest finish is the smallest latest start time of all of its successor tasks. So whichever tasks are dependent on that task before they can start, the latest finish of that task is the smallest of those latest start times of all those successors. So we start with the 13 weeks, and this becomes the latest finish time for E and F. After all, these are the end tasks. These are the finished tasks. These are the tasks that are at the very end of the project. And since nothing is waiting on these tasks have a latest finish time of the project completion time of 13 weeks. So what do we do now? Well, we start calculating the latest start times for each of these tasks. For E, latest start time is going to be latest finish time of 13 weeks minus a task length of 5 weeks. So 13 minus 5 is 8. For task F, we have a latest finish time of 13 weeks. 13 minus 3 is 10. So We go on. For task D, well, task D is the predecessor to task F. So task F's latest start time becomes task D's latest finish time. So that 10 weeks, that's task F's latest start time. This becomes the latest finish time for task D. We go on. We calculate task D's latest start time. So 10 minus 3 is 7. And this becomes task D's latest start time. Now here's where things get interesting, because task C is a predecessor for both task D and task E. So how do we find the latest finish time for task C? Well, you take the smaller of the latest start times for task D and task E. So task D has a latest start time of 7 weeks. Task E has a latest start time of 8 weeks. So task C has to finish before all of that. So task C's latest finish time becomes the smaller of the latest start times for task D and E. So that 7 weeks of task D, since it's the smaller of the two, this becomes the latest finish time for task C. Now, once we have the latest finish time for task C, we can calculate latest start. 7 minus 3 is 4. And from here it becomes fairly straightforward. Task B only is the predecessor of task D. Task A is only the predecessor of task C. So task D's latest start time becomes task B's latest finish time. That's 7 weeks. And task C's latest start time of 4 becomes task A's latest finish time of 4 weeks. And thus, we're able to calculate the latest start time for task A and task B as well. For task B, latest start time is 7 minus 5 is equal to 2. For task A, latest start time is 4 minus 4 is equal to 0. So, we've filled in our project flow map. So, what's left? Well, what's left is to determine a few things with regard to each task. Specifically, we want to determine slack, and ultimately we want to determine the critical path. So, the slack, this is just the amount of time that a task can be delayed without delaying the entire project. So, it's wiggle room. It's how much we can delay things. It's how much we can procrastinate a task without causing a delay in the entire project. So for any given task can be calculated one of two ways. Either latest start time minus earliest start time, or latest finish time minus earliest finish time. Either one works if you've done the math right. So we calculate the slack for each task. Now here's where things get interesting. You see that task B and task E, these have slack of 2 and 1 respectively. But you see that there's a lot of tasks here that have 0 slack. And it's important to note what's going on here. So, task A, it starts up, right away, goes 4 weeks. Once task A finishes, task C starts. It starts at week 4 and goes for 3 weeks, so it goes from week 4 to week 7. Then once task C is finished, task D starts, and it takes 3 weeks, so it goes from week 7 to week 10. And then once task D is finished, task F starts, and that goes from week 10 to week 13. So, how long does this project take? 13 weeks. This is not an accident. The reason why is because that 13 weeks is created by that critical path, by that set of tasks that caused that 13 weeks, that developed that 13 weeks. So, tasks A, C, D, and F have a slack of 0. They cannot be delayed without delaying the entire project. And it is this path of tasks that we call the critical path. So, the critical path is this path of tasks for which no delay can occur without delaying the completion of a project. Any delay along the critical path will delay the completion of the project. All the tasks in the critical path have a slack of 0. In fact, that's how you determine if a task is on a critical path. Does it have a slack of 0? Now, there can be more than one critical path, and we'll see examples where there is more than one critical path. But there must always be at least one critical path. If there's not at least one, then something went wrong with the math somewhere. Okay, so here's our critical path, A, C, D, F. This is the set of tasks that is going to determine how long the project takes. This is a set of tasks that must start right away, that cannot be delayed. So, when managing, how much attention should you give to these tasks? Well, you need to be sure that these tasks occur on time, that these tasks are not delayed, because to delay them would delay the entire project. So, it's a management tool. At any rate, sorry this particular video took so long. Just, well, kind of needed to walk through all of the steps on PERT CPM in this case. So, be well, take care, and have a good evening.